Our fifth project is also educational material development. It's by Israel, and he's from Mexico. Okay, Israel, it's your turn.
Thank you, Professor. Thank you, everybody. I'm happy to be here, and thank you, QWorld, for the invitation and for the wonderful Q course. People that are not familiar with quantum computing may wonder what is quantum computing, right? So quantum computing lies at the intersection of physics, mathematics, and computer science. In these links, you can get to the repository of the work I'm going to present and a video presentation with more details of the contents. So, as this is an introductory work, it is natural that the readers may wonder, what kind of math do I need to learn or do I need to know to learn quantum computing? And the short answer is actually not that much as one would expect. There are introductory workshops that require no more than high school math in order to start learning. But if the readers have a STEM background, they may already know the basics of quantum computing without being aware of it. So this is the aim of this work. If they are serious about learning the theory behind quantum computing, they will benefit a lot by knowing some linear algebra concepts such as vectors, matrices, their manipulation, vector spaces, linear operators, eigenvalues, eigenvectors, and so on. But if they are not familiar with these concepts, not everything is lost. I am sharing here a couple of great resources to get acquaintance with linear algebra. What else? They will also feel at home if they already know some trigonometry, basics of probability and complex number. And again, I'm sharing some resources if they feel the need to better understand these concepts before diving into quantum computing. The current work revisits all these concepts, but it is not intended as a first approach. The reader will benefit more if they already have a first touch with these concepts beforehand. Okay, so if I'm already familiar with these concepts, where do I start? There are this couple of great workshops by QWorld, the introductory Q Bronze and the intermediate Q Silver. Actually, I completed these workshops before entering Q course, and that helped me a lot to better understand and to be able to complete the course. So I really recommend to take them. There's also this nice IBM Qiskit textbook. Qiskit is a quantum computing framework, and it is really nice explained inside there. So these are both your theoretical and practical resources. So the readers will enjoy more this journey if they are already familiar with Python, but not necessarily high level Python, as we had one question about that, or even any other programming language. There are also frameworks working with other languages like Q#, that is from Microsoft. So any familiarity with programming is very valuable. Okay, so what is different in this work? The notebooks in this repository are intended to have an emphasis on the mathematics and the physics behind quantum computing. And all the exercises can be worked out with pen and paper. So no special software is required beyond the ability to run Juputer notebooks. Also, most of the sections have worked examples and exercise along with their solutions, so readers can easily validate their understanding. In the first section, I give a short introduction, quick motivation of why we need quantum computing. And then all the core concepts are presented. They will be the basis for all the mathematical development that will be done in all the next sections. Most of these concepts come from linear algebra, as I already explained. So if the reader has not taken a first course on linear algebra, please refer to the great course from Professor Gilbert Strang and the couple of resources I just shared. So in the mathematics for quantum computing sections, concepts such as Hilbert space and dual space are reviewed. Then Dirac notation is introduced. This will be helpful to ease all the work that will be done in the next sections. Also, the block sphere is presented and explained as a geometric structure that emerge from the physical restrictions that are imposed on the vector space just reviewed, in order for that vector space to represent the state space of a two-level system. So with this, a qubit is defined to be precisely a point on this sphere of radius 1. Sorry. Next, some concepts are that are associated with linear operators are presented. Such concepts as a joint operator, self-adjoint operator, unitary operator. Also, in the spectral theory notebook, the reader will see that eigenvalues are in fact elements of something called a spectrum of a linear operator. They will also learn what is the multiplicity of an eigenvalue and why it is important to have that in mind. We will review the general Heisenberg principle, and we will focus or emphasize that this principle holds for any two self-adjoint operators. And when we particularly take them to be the position and momentum operator, this gives place to something more particular, but also more familiar, that is the Heisenberg uncertainty principle that is known in physics. And in the next notebook, the Pauli operators are defined. We also derive their matrix representations and see them as outer products and see several properties that will be useful. The next two sections address the physics component. The first one is a very short introduction to quantum mechanics and how we can use the tools, the mathematical tools developed in past sections to understand important physical concepts, such as time evolution and wave function collapse and so on. Next, quantum entanglement is a core concept in quantum computing, so it deserves its own section. And at this point, all the theory that we have developed so far is summarized. We detail a fully worked example of what we can do with all this tooling. We start by making sure we have a valid initial state. We calculate the normalization constant. We also see that what are the possible values that we can get from measuring an observable, and with what probability we can get them at an initial state. We'll also use the time evolution operator to understand what is the state of the system at an arbitrary time t. And we also see what is the probability of measuring each eigenvalue of an observable at an arbitrary time t. Finally, we use a projector or a projective measurement that Alvaro just mentioned to understand what is the status of the system immediately after making a measurement. And at this point, the reader will be doing basic quantum mechanics. That's cool, right? Now, at this moment, it is to start doing actual quantum computing, and concepts such as quantum register and quantum circuits are defined. Quantum gates are defined as unitary operators, and we discuss what is the rationale behind it. Also, we present the most common types of quantum gates. We also study Hadamard gate, and we conclude that we can think of it as a base change operator between Pauli operators sigma c and sigma x. Also, some results related to single qubit gates are given and used as a motivation to see that to build any single qubit gate, we will only need a Hadamard gate and rotations around the z-axis. Finally, this work is rounded up by the Solovay-Kitaev theorem that allows us to answer a critical question in quantum computing. This question is, can we have a finite computational universal set of quantum gates? This is really relevant because that would allow us to have to implement physically only a finite set of quantum gates and build up all others upon this computational universal set. So if you want to know the answer, please take a look at these notebooks and discover it by yourself. Also, if any of the readers is interested in continue learning quantum computing and contribute to this work, there are several topics that can be worked out, such as quantum algorithms, quantum protocols, quantum memory corrections, among others that have been mentioned in this webinar. So with that, I can only thank you for being here. Thank you very much. Do you have any questions?
Thank you, Israel. So any question?
Yeah, once again, just a small comment. Thanks you to both of you for trying to create some more teaching material, because we always need more, so much more teaching material. So thanks so much for working on that.
Thank you.
We had a couple of more, only we have limited time. We didn't invite all. I think quantum chemistry, introduction to quantum chemistry, one project, quantum walks, another project, if I remember. If you visit webinar page, you can go to course page and you can see other project as well. So Israel, you plan to continue also still on this project?
Yes, definitely. I actually started working and continue working in this project because I am going to use this materials as part of my undergrad thesis. So I definitely want to continue to make it more robust.
Okay, very good.